Hello again. This is a continuation of the parametric equations topic. The last video just gave you some general idea of what parametric equations are like when they're used, but now we're really going to get into actually how to do calculus with parametric equations. Some of the particular calculus applications that you're going to see are finding the slope of the tangent line, area, arc length, and surface area. And on this first page, you could just see a general summary of how you would do each when faced with a set of parametric equations. Often parametric equations have a parameter of t. You'll see an example where the parameter is theta. So while t is most common, don't necessarily get fixated on that particular letter. All right, but let's just jump right into it and take a look at problem 1. Now for these problems, I have already done the solutions, and so I'm just going to talk you through the solutions, but feel free to pause the video at any point to either copy it down or make your own notes with what I'm saying, not just what I've written. So in the first problem, the parametric equations that are given, and you could ignore the 1, 2, and 3. That's just past writing that I forgot to edit out. We want to find the two tangent lines at the point 3, 0. So the first thing is to figure out, well, what is the slope of the tangent line at that point? Now dy dx is what we need because we learned back in Calc 1 that is the slope of the tangent line, but y is not a function of x. They're both functions of t, and so you need to somehow get dt in there, and the way you do that is by rewriting dy dx as dy dt over dx dt. So we need the derivative of y with respect to t, which is 3t squared minus 3, and the derivative of x with respect to t, which is 2t. You can manipulate this, factor out a 3 on the top, and realize t squared minus 1 factors further into t minus 1, t plus 1, which is what I've got over here. And we want to know, okay, so when x is 3, we need to figure out what t values are we investigating. And so when x is 3, that means t squared is 3, which when you solve for t means t is plus or minus root 3. When you try to satisfy y being 0, t cubed minus 3t is 0, but t cubed minus 3t factors into t and t squared minus 3, and that product is 0 when either one of those multipliers is 0, so either t is 0 or t squared minus 3 is 0, which means t is plus or minus root 3. Since the only numbers that are satisfied for both x equals 3 and y equals 0 are plus or minus root 3 for time, those are the two values we are going to investigate for the slope to get our two tangent lines. So when t is root 3, dy dx is going to be positive root 3, and I just substituted root 3 in for t into the box, the red box that I have. And when t is negative root 3 and you sub that into the dy dx formula for t, you end up getting negative root 3. They don't have to actually yield themselves. This problem does work out that when t is root 3, the slope is root 3, and when t is negative root 3, the slope is negative root 3. So that's just how it is for this problem. That's not a rule of thumb. And then we need to actually find the equations of the tangent lines, and you could either use y equals mx plus b form, or the point slope formula, which I have written next, y minus the y coordinate equals m times x minus the x coordinate. And so that's the version that I went with. So y is 0, x 0 is 3, and the slope is plus or minus root 3. And so when you plug in, you get the black box, which are your two equations for tangent lines at the point 3, 0. Part B wants us to determine the points where the tangents are horizontal or vertical. Horizontal means the slope is going to be 0, and so that is the first detail that I'm investigating. So that means that this formula of t has to be 0. And that's only going to happen when the numerator is 0, which is only going to be when t is plus or minus 1. So when t is 1, and you plug that in for x equals t squared, that means x is 1. And when you plug 1 in for y equals t cubed minus 3t, you end up getting negative 2 for y. You do the same thing when t is negative 1, and you end up getting x equals 1 squared, which is 1, and y equals negative 1 cubed minus 3 times negative 1, which is positive 2. And so your 2 points for horizontal tangents are 1, negative 2, and 1, positive 2. The vertical tangent lines are going to be when the slope is undefined or plus or minus infinity, and that's only going to be when the denominator is 0, and so that is when t is 0. And when t is 0 and you plug into the parametric equations, you get x equals 0 and y equals 0, which is the origin. And so those are your 2 horizontal and 1 vertical tangent lines, or the points at which you have those tangent lines. Part C wants us to investigate concavity, which is the second derivative, which means that we want d dx of dy dx. But we know that those are functions of t, so we need to get t in there. So d dx is also the same as d dt over dx dt. And you still are taking that or acting on dy dx. And we have that dy dx we already had found is 3/2 t squared minus 1 over t. We had factored t squared minus 1 into t minus 1, t plus 1, but it's fine to put it into this form here. And dx dt, where x equals t squared, is just 2t, so that's on the bottom. You cannot bring that into the derivative on top, at least not yet, not until after you've taken the derivative of the numerator. When you do that, you get what I have on the top line on the right side. And when you simplify, you end up with 3/16 of t squared plus 1 over t cubed. And we want to know, when is this 0 or undefined? And it's never going to be 0, because, at least not for real numbers, because t squared plus 1 is only going to be 0 for imaginary. And so there is no case, since we don't care about imaginary numbers here. But it is undefined when the denominator is 0, and that's going to be at t equals 0. So then you do the second derivative test, and I tend to do by creating a number line. So I did a quick sketch of a number line. I put the t value of 0 on there. You need to check whether the second derivative is positive or negative to the left of 0 and to the right of 0. So you just pick any value on either side. I use -1, +1 when t is -1, and you plug that into what I highlighted in yellow here. You're going to get a negative value. The top is positive, but t cubed will be negative. And when you do the same for when t is +1, you get a completely positive value. So we know that the concavity is concave down before 0, but concave up afterwards. Problem 2 investigates the area of the region enclosed by the curve or the parametric equations in example 1 that we just went through. I did a quick sketch of what that region looks like. It's kind of like the right half of it, of an infinity symbol. It is symmetric. My picture isn't, but it should be. And the area is the integral of y dx, so you just substitute in y is t cubed minus 3t, and dx, well, x is t squared, so dx dt is 2t, and when you solve for dx, you get 2t dt. Now, notice that with respect to x, our limits of integration were from 0 to 3, but when we converted into the time domain, and we learned back here that time, we have these two tangents between plus and minus root 3. So time is going to be between those two values. You could do like we did in the last video and figure out the path that it's taking, and understand why the positive root 3 is on bottom and the negative 1 on top. If you don't see it, you could always switch them, and when you get your answer, you're just going to have a negative value, which should ring a bell and say, okay, I must have my bounds flipped. And so that's all having a negative answer is going to mean, is that you probably switched them. So, but by symmetry, I could just do 2 times just half that interval, and so I went from 0 to negative root 3. And this polynomial is pretty easy to integrate, so after you integrate and you evaluate, you get the answer of 8.314 for the area. Problem 3 is looking at arc length, and this is arc length of a particular cycloid for theta between 0 and 2 pi. And so the arc length is given by the formula that I've written here. It doesn't matter whether you do dy d theta squared plus dx d theta squared or vice versa. The order for addition won't matter. And so when you take the derivative of x and y with respect to theta, dy d theta, well, you've got r minus r cosine theta. R is constant, so the derivative of the first term is 0, but the derivative of the second is going to be r sine theta, which we want to square. And the dx d theta is going to be r minus r cosine theta, which we want to square. Now I see that I'm going to get an r squared from both of those terms, which I can bring out of the square root as r. And when I expand, I have a sine squared plus 1 minus 2 cosine theta plus cosine squared. What I've underlined in green is an identity, sine squared plus cosine squared, and we know that to be 1, which is why this then becomes 2 minus 2 cosine theta, and I factored out the 2 in the next step. Now, to figure out how to solve this one, I used a little trick, and that is coming from an identity, and I've got that over here in blue. So the identity is cosine 2x equals cosine squared minus sine squared. I am going to convert this into just sine squares on the right, so cosine squared is 1 minus sine squared, and then you are subtracting a sine squared from that, which is where the 1 minus 2 sine squares came from. But I have a 1 minus cosine theta inside my square root. So I want a 1 minus cosine form. So I am going to subtract the cosine 2x to the right and add the 2 cosine squared to the left, which gives me the arrowed line there. And then I want 2x to really be theta. So if theta is 2x, I'm going to have 1 minus cosine theta, but that means x is theta over 2, so I have a 2 sine squared of theta over 2. Now that our integral has 1 minus cosine theta, I know that that is equal to 2 times sine squared of theta over 2. So I make that substitution. I'm going to have a 2 times the 2 that's inside the square root. So that's the square root of 4, which is 2, so that's where this 2 came from. And then the square root of sine squared is just sine. And the integral of sine of theta over 2 is 2, or negative 2 cosine theta over 2, which is where my -4 comes from, because there's a 2r up front. And I want to, again, evaluate this over the full support of theta from 0 to 2 pi. And when you do that, it simplifies to 8r. And then the final example is a surface area one. So we want the surface area of the sphere given by these parametric equations across the x-axis. Now at the initial time of 0, cosine of 0 is 1, sine of 0 is 0. So starting at 1, 0, like I have in my diagram, I chose a few other points, and I realized that from 0 to pi over 2, we are heading in a counterclockwise direction. I only need the top half because, as the instructions say, we are rotating about the x-axis, so that's going to give us our spherical shape. So it's really from this picture that I discovered what the integration bounds should be, 0 to pi over 2. Now, plugging in to the surface area formula, we've got 2 pi y times the square root of dx dt squared plus dy dt squared. And so here we have 2 pi, y is sine 2 theta, and then dx dt is going to be -2 sine 2t, which we are squaring, and dy dt is 2 cosine 2t, which we are also squaring. And so that is going to give us, inside the square root, 4 times sine squared plus cosine squared, and that's 1, so we really just have the square root of 4, which is 2, and that's going to multiply by the 2 pi up front, so that's why I have 4 pi, and the sine 2t up front is still lingering, but at least this is easier to integrate, and so this is going to be -1/2 cosine 2t, which gives us -2 pi cosine 2t evaluated from 0 to pi over 2. And when you do that, it's going to come out to just 4 pi. And that is how you could do some calculus